Hello. In this video, we're going to be looking at solving 2D motion problems or kinematics problems, which is a common starting point in introductory physics. And you'll encounter what seems to be a lot of different equations of motion, but they can really be broken down into a pretty small set. And I'm going to go through a general process you can use for solving these kinds of problems. First, you start out with the most general equations of motion, the equations that are always going to hold true for these kinematics problems. Then what you'll do is read through the problem description, sentence by sentence, phrase by phrase, and identify those variables specific to the problem. And once you've done that, you can insert those specific variables into the general equations of motion and then go about solving for those unknowns. So let's look at those general equations of motion. In kinematics, when you start out, you're operating under the assumption that your accelerations are constant. And so when you have a constant acceleration, that means the final velocity is equal to the initial velocity plus that acceleration times time, and the final position is equal to the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. So you'll have that set of equations for the x direction and that set of the equations for the y direction. You just have different constants in there, different constant accelerations, different initial velocities, and different initial positions. But these equations are always going to hold true for these kinds of motion problems. You may have encountered other equations of motion, but they're just combinations of these base ones in different ways. Maybe you substitute out the time, or maybe you're operating the assumption about what a final position or final velocity is. But these equations, this set is always going to hold true. When you go about finding the variables specific to the problem, you want to take your time, read through the problem carefully, look through it phrase by phrase. But here are some tricks and tips that you can use for making those identifications. First off, and this may seem like overkill at first, is just to identify what x and y mean in that problem. It could be that x means horizontal and y means vertical, or let's say if you're moving, let's say a billiard ball across a table or a boat in the ocean, you could have a north-south movement versus east-west movement. But it's important to identify what x and y means, because I can't tell you how many times I've run across a student who suddenly says that someone going north and south is also being pulled south with the acceleration due to gravity. So just always be sure you know what x and y mean for the problem. When you look at the initial positions, if nothing is given about where you start out, you can safely set the initial positions to be 0, because your final position is always in relationship to that. So if you start nowhere special, just say you start out at x equals 0. If you're looking at a case where there's vertical motion, I typically set the ground level to correspond to y equals 0. And if you're looking at projectile motion, the highest point corresponds to the velocity in the y direction to be equal 0, because at that point you're done going up, you're done having a positive y velocity, and about to go down, you're about to have a negative y velocity. So at the very top, the velocity in the y direction is 0. Also, in projectile motion, if there's no mention about crosswind or sidewind or friction, you can safely set the horizontal acceleration to be 0, and you can set your vertical acceleration to be gravity acting downwards. A lot of times you'll see the initial velocity or perhaps the acceleration given in terms of a magnitude and angle. In those circumstances, you want to apply your trig identities to get those initial velocities and accelerations in terms of their x and y components. And you can always rely on the base definition of those trig identities, where the sine is always equal to the opposite side over the hypotenuse, and the cosine is always equal to the adjacent side over the hypotenuse. Once you've identified those specific variables, then you can insert them into your general equations of motion again, and at that point you can solve for whatever the unknowns are that are being asked for in that problem. So let's go through an example where you can see how this plays out. We'll do a pretty common projectile motion style problem. So let's say we have a cannonball is launched from ground level pointing south at an initial velocity of 20 meters per second at an angle of 30 degrees. And we'll look at two scenarios, one looking at how high does it go and how far to the south does it land. So I put the general equations of motion before. Let's just jump into identifying those specific variables. So I have the problem description up top so we can reference it. So we have vertical and horizontal motion taking place. So let's say that the x direction corresponds to the horizontal and the y direction corresponds to the vertical. Since our cannonball is being pointed to the south, I'll say the plus x direction is the south, minus x is north, and plus y is up, and minus y is down. Again, just distinguishing between the horizontal and vertical motion. We start at ground level. That's the first phrase that's stated. So we'll say our initial y position is 0, and there's nothing special about where we start in the horizontal, so we can say our initial x position is 0. There's no friction or crosswind mentioned, so there's no horizontal acceleration, and our acceleration in the vertical is just gravity acting downwards, minus g, or minus 9.8 meters per second squared. So again, we just go through it phrase by phrase, being mindful of what we mean for the x and y directions. In this case, x is horizontal, y is vertical, so x will equal, positive x will equal south, plus y is up, and minus y is down. So let's look at the initial velocity. So the problem says that the cannonball is launched from ground level pointing south at an initial velocity of 20 meters per second at an angle of 30 degrees. Whenever you're given a vector like this in terms of a magnitude and angle, it's useful just to draw out that vector. So this is an illustration of just the initial velocity. It's not the trajectory of the particle. But here we have the initial velocity. It's 30 degrees above ground, and it has a y component and an x component. So we're going to use our trig identities to get those components. Well, the x part of the initial velocity is the adjacent side of the angle, so that means we're going to use the cosine. Cosine is adjacent over hypotenuse, so the cosine of that 30 degrees is the adjacent side, the initial velocity in x over the magnitude. Multiplying both sides by the magnitude, we get the initial velocity in x is the magnitude of the initial velocity times cosine of 30 degrees. So that would be 20 meters per second times 0.866, giving us an initial velocity in x of 17.3 meters per second. We're going to do the same thing to get the y part. The y component of the initial velocity is the opposite side of that angle, so we're going to use a sine. Sine is always opposite over hypotenuse, so sine of that 30 degree angle is the y component of the initial velocity over its magnitude. Multiply both sides by the magnitude, we have the initial velocity in y is the magnitude of the initial velocity times sine of 30 degrees. So that would be 20 meters per second times 0.5, giving you 10 meters per second for the initial velocity in y. Again, if you're given a vector like this in terms of the magnitude and the angle, just sketch out that vector. It's not the trajectory of the object, it's just a picture of that vector, in this case the initial velocity, and then you can use your trig identities to separate that out into its x and y pieces. So we've read through everything in the problem. What we need to do is insert those specific variables we've identified into the general equations of motion. So I've put up the specific variables we've identified up here. Next, we just have to insert those into our equations. When we do so, we end up with the equations of motion specific to this problem. And what these equations tell us is what's going on with the velocities and the positions at any given time. So we can look at particular times or particular locations and solve for those unknowns. So again, all we did was insert those specific variables we identified into our general equations. So what happens in a lot of physics problems is the problem is really in the setup. So we haven't actually gotten to where the problem is asking. We've just identified the background or the scenario for that problem. Once we've done that, our work is pretty much done. We can just fiddle around with the equations for whatever is being asked. So the first thing that was asked was, how high does it go? We need to interpret that in terms of our equations of motion. So the first thing that was asked was, how high does it go? And we need to interpret that in terms of our equations of motion. And how high, that means what's our y position, and at the highest point is when it's done going up and about to go down, so the velocity in the y direction is equal to 0. So we're eventually going to figure out, again, what the y position is when the velocity in the y direction is 0. So what we'll do first is use the velocity in the y equation to find the time, and then use that time to get the y position. So we set our y velocity equation that we identified previously, and just set that equal to 0. And when we solve for the time, we end up with time is 1.02 seconds. Then we can insert our time into the y position equation that we identified earlier. And when we punch through the numbers, we end up that our final y position is 5.1 meters. That's how high it goes. The second thing that was asked was, how far away does it land, or how far to the south does it go when it lands? So when it's asking how far to the south, that's a horizontal position. So we're interested in the final x position when it's at ground level, while ground level corresponds to the y position equaling 0. So we're going to use the y position equation, set it equal to 0 to solve for the time, and then use that time in the x position equation. So we use the y position equation that we solved for earlier and solve for the time. When we do that, we get a time is 2.04 seconds. And then we can insert that time into the x position equation that we solved for earlier, and we end up with the final x position is 20.4 meters. Again, the bulk of the work is in the setup, just getting those equations of motion. And once you do that, you can solve for any of the particulars of the problem. So the general process is, again, start with the general equations of motion for the final velocity and final positions. Then you read through the problem carefully, try to identify the variables specific to the problem, identify what x and y means, and if you're given, say, the initial velocity in terms of the magnitude and angle, using your trig identities to separate that out into its x and y components. Once you've done all that, you can insert those specific variables into the general equations of motion and solve for whatever the unknowns are being asked. So I hope you found this video helpful. I'll be posting some more videos in the future.